All right, let's try this again. So we're going to talk about colligative properties today, specifically the calculations that go along with it. So I'm going to jump over to this nice little table here. Hi, sorry. Okay, so colligative properties, specifically we're going to talk about freezing point and boiling point. So what happens is when you have an ionic substance such as, let's go AgCl, when you put it into water, and this is something you don't really want to put in water, but we're going to go with it right now. When you put it in water, the Ag and the Cl will actually go ahead and break up. So you've got the Ag floating around and you've got the Cl floating around. Now let's say that you put something like sugar. So sugar is C6H12O6. That's one of the sugars anyways. So when you throw this in water, this guy will stay as one molecule, C6H12O6. So this guy doesn't break up, this guy does. So why is that important? So when water freezes, it makes these really nice little crystals. And so we're going to erase this. Okay. So the issue with that, though, is let's say that you had a Cl in the middle. Well, now you've just interrupted that process of making solid water. This guy blocks it. So basically what happens is when you throw an ionic, or when you throw anything in water, it is going to kind of mess up that freezing process. Same thing with boiling. So when something is boiling, well, we know that we add temperature and the molecules go faster and faster. So here we've got water. I'm just going to draw circles for my water molecules. So you've got these water molecules and they are moving really fast. They're moving really fast. Eventually they'll have enough energy and they will actually break out and leave in the form of gas. The issue here, so we know water looks like this. All right, so this side is a little bit negative. These sides are a little bit positive. Okay, so let's say that you do have that Cl minus here. Well, we know that positives and negatives are attracted to each other. So what happens is there's this kind of attraction here. And there's an attraction here. So what happens is the water will actually be slightly attracted to your ions in here, and so it will make it harder for it to leave. All right, so the ions do a lot. Now, these molecules, they also do things, but there's only one of them, so they can't screw stuff up as much. So they're going to have less of an effect. All right. So the first thing I want to talk about is something called the Van Hoff factor. So sounds big and scary, not terrible. All the Van Hoff factor is when you put a substance in water, how many things are you going to get out of it? So for example, we said that AgCl, when you put it in water, it becomes Ag plus and Cl minus. So how many things do we get? We got 1, 2 things. This would have a Van Hoff factor of 2. Not terrible. Okay, what about, let's do MgCl2. Now in this case, you've got 2 chlorines. So we've got Mg, 2 plus. Remember, you can get these charges on your periodic table. plus 2 Cl minuses. In this case, we've got 1, 2, 3. So this one has a Van Hoff factor of 3. Not terrible. Now, these, if we look, these are both ionic. Metal, non-metal. What happens if we use something covalent? So let's go back to that sugar, C6H12O6. Well, in my drawing, we didn't break it up. Sugar stays a molecule. So this one, when you throw it in water, it's going to look exactly the same in molecule form. In this case, we only have one thing. This guy then has a Van Hoff factor of 1. All covalents will have a Van Hoff factor of 1 because none of the covalents are going to break up for you. So that's kind of a nice trick. All right. Covalents. Okay, now, why is this important? So if we have our Van Hoff factor and we have the molality, we're actually able to calculate how much our boiling point or freezing point will be affected. So let's go ahead and do that. Okay, so let's say I throw 5 grams of NaCl in, let's do 20 grams of water. That's a lot in there. I don't know if that's possible. Okay. So we have 2 very special equations to help with this. So the first one, the change in the temperature for the boiling point is equal to your Van Hoff factor times your constant for your boiling point times your molality. So I'll label that. Okay, Van Hoff factor, constant, molality. Okay, so the constant, whenever I ask you for any kind of calculation, I will give you a table. It looks identical to this. You'll find it on the second page of your worksheet for homework. So first thing, let's go ahead and find that Van Hoff factor. So we're working with NaCl. So how many things can NaCl break into? I'm counting 1, 2, right? Na plus and Cl minus. Okay. So, sorry, I'm specifically looking for the new boiling point. Okay. So if we were going to do this equation, the change in our boiling point is equal to 2 times this constant. So let's go ahead and look up here. So we're working specifically with water right now. Now, all of these are solvents that we can use, but right now I'm just going to work with water. So right here, we've got that Kb. So our Kb is 0.51. 0.51, okay? Last thing we need is our molality. Now, fortunately, we can do that one pretty easy, right? Okay, so we've got 5 grams of NaCl. We're going to look on our periodic table for that molar mass, which I think is 58.4 something. Yes, 58.44. So we've got 58.44 grams per 1 NaCl. I really miss you guys being able to calculate this for me while I talk. Bummer. Okay, so we have got 0.0856 moles of NaCl. All right, now we just have to get this 20 grams of water into kilograms. We have 20 grams we know that there are 1,000 grams per 1 kilogram. So we're looking at 0.02 kilograms. We remember from yesterday, I should have given myself more room. Molality is equal to moles over kilograms. So my molality is 4.3. Okay, so we're going to do 4.3. I'm back over here now, sorry. So we're going to do 4.3 times 0.51 times 2. I have got a change in the temperature of my boiling point of 4.36. So did I find my new boiling point yet? No. I found the change in my boiling point. Now, fortunately, on your handy dandy table, you know that the normal boiling point of water is 100. So normally water boils at 100 degrees. We changed it by 4 degrees. So our new boiling point is 104.36 degrees Celsius. And that's the problem. Okay. Now there is one more equation. So again, this is specifically for boiling. If you look, there is also data for freezing point up here. There you go. Okay. So the freezing point data. The equation for freezing, it looks very familiar. Your change in temperature for your freezing is that Van 't Hoff factor again, times this time your freezing constant. You'll notice this is negative. And that molality again. So looking at the same problem, we had that 20 grams of NaCl we had 5 grams of NaCl in 20 grams of water. This time, let's find the new freezing point. Okay, so I'm going to pull a lot of the data we did earlier. So that Van 't Hoff factor hasn't changed. That's still 2. We like our freezing constant this time and go all the way down here. So we are looking at negative 1.86. And our molality from last time was about 4.3. So again, I am just pulling these numbers from earlier. If you don't know how to find this number or this number, go back to the boiling point section. So we're going to go ahead, we're going to multiply these out. So my change in freezing temperature is 2 times 4.3. Okay, so we got a significantly larger change in our freezing temperature than we did earlier. I got about negative 16 degrees. Okay, so in this case, and this is nice, water usually freezes at 0. We're freezing at 16 degrees below where it normally freezes. So in this case, we are going to be freezing at negative 16 degrees Celsius. So, yeah, that's how to do the calculations. That's how to, or just how it works in general. And yeah, if you have any questions, feel free to email me. Office hours are at 11. Yeah, all right. Have a great spring break, guys. I'll see ya at some point. And stop recording.